Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here. What we're doing today is engineering calculus tutorials. Chapter 0 is going to be things you should already know. Basically, this is going to be they push us to appendices or something like this, and everything that you've done from K to 12, which is in varying degrees of intensity. We expect that you know all of these types of things. What are real numbers? What is the Cartesian plane? What is trigonometry and all these types of things? We're going to go over these in this first chapter, which is chapter 0. Then we'll get to all of the engineering things that we're supposed to have. Section 0.1 is going to be the set of all real numbers, and then we'll go from there. This lecture specifically, what we're going to do is look at different types of real numbers and their more prevalent avatars. Let's get to it. Okay. All right, we're going to discuss the real numbers. Before we start this, I always ask, and so you can think to yourself, pause if you want, what is the set of all real numbers? Don't give me an example of a number. E pi is a real number and 2 is a real number. Can you describe in your own words what the collection of all real numbers is? Exactly. We do calculus of real numbers, which is functions, derivatives of functions of real numbers, and nobody knows what a real number is. So let's wind it back. What are real numbers? Then what are functions? Then what is the derivative of a function of real numbers? This is where we're going with this. What is a real number? In order to discuss a real number, we need the notion of a set, because we're going to get different groups of a Matryoshka-Doll of nested sets, and then eventually we'll stop at the real numbers, and then that set that diagram keeps going. Complex numbers, Hamiltonian numbers, will get higher dimensional. But to describe the collection or the set of all real numbers, it would be nice to know what a set is. So intuitively speaking, not the rigorous set theory axiomatic definition of what a set is. Intuitively speaking, a set is a collection of objects. Put apples in a basket. The basket is the set. The objects are going to be called elements, the apples inside there. The notation we're going to use is, classically, we're going to use lowercase letters for the things in the set and capital letters for the sets themselves. And this fancy E is going to be read as it's in there or an element of. So this, as an English sentence, is the short way of saying the element X is in the set S. This, how do we say not equals? We put a dash through it. So how do I say not in there? We put a dash through the fancy E, or element of, and this says X is not in that set. So now we have notation for elements, little variables, X, Y, Z, A, B, C. We now have a notation for sets, capital letters, A, B, C, capital A, or S, T, U. And then what we're going to try and do is show that the real numbers is the disjoint union of the set of all rationals and irrationals. And so we need a few operations on sets. How do we combine sets? Just like how do we combine real numbers with addition? You add them, 2 plus 3 gives us a new guy, 5. When I have two sets, are there operations I can create to get other ones? And yes, you're going to use intersection and union often in calculus. In particular, when we look at domains, I have a set of real numbers of this domain and a set of real numbers for this other function, which is a subdomain. And then if I want to add those two functions, the domain is the intersection of the original two sets. So what are these operations we're going to do on sets? All right, definition. Given two sets now, we want operations which will create new sets from given sets. You can think of this as an analog to, I have the number 2 and the number 3. I can do 2 plus 3, which will give me another number 5, or I could do 2 times 3, another operation, which will give me a different number 6. I have different ways of combining them and algebraic notation for these. Now, if I am given two sets, S and T, there's the two most common things we're going to do, but I've got the 5 classical definitions we want from a generic set. The union in your language is going to be the cup symbol, and that's going to be the word or in our language. So the union of two sets creates another set, S union T, which is the new set of all elements, which is in S or in T. So it can be in either one, or is union. The intersection of two sets creates another set, and in general is smaller because it's going to be denoted S cap T, and it's a new set which is all elements which are in both S and in T. To get in the union, you have to be in S or in T. To be in the intersection, you have to be in S and in T. So union is or, intersection is the word and. And then the other things we need are, classically, we're going to just consider subsets of the real numbers, so we should know what a subset is. S is a subset of T, denoted S, now sideways U, if all the elements of S are also elements of T. Immediately using our notation from the previous scene, we have if X is in S, that implies X is in T. So this symbol I'm already sneaking in there. If you haven't seen before, that means implies. Technically, there's a universally quantified statement here for all X. If X is in S, then X is in T, but I'll spare you this universal quantification for now. 4 is, now if I have subsets, if S is a subset of T, the complement of S in T is the other part, things that are in T that are not in S. You'll see that the real numbers are the rational numbers and their complement, the irrational numbers. And then the empty set. Why do I want the empty set? Well, the empty set is the set with no elements in it. This seems obvious, but what I want to do is the intersection has to always create a set. But what happens when I intersect two sets that have no common elements? What set am I creating? I'm creating the set with no elements in it, so their intersection will be the empty set in some cases. Let's do at least one example. This will come in full force when we do intervals, because every domain of a function is going to essentially be an interval. And then when I start wanting to combine functions f plus g, what's the domain of f plus g? The intersection of the domain of f intersect the domain of g. So we're going to have this intersection business when we have intervals. For right now, I'll do a discrete example. All right, example 1. Also, we're going to use set builder notation eventually. I'll get into that a little bit, but right now sets are baskets essentially, so we're going to use curly bracket to say that the set S is the first 7 positive integers. Right now I won't start with any fancy numbers. We'll just start with a collection of S has 7 things in it, 1, 2, 3, 4, 5, 6, 7. T is the first 3 positive even numbers, 2, 4, 6. And then same thing, R is 3, 5, 7, 9 odd numbers, not including 1. But what we're going to do with this is try to look at what these symbols mean intuitively and just use the definition of each one with these 3 combinations of sets. In particular, we'll do intersection with the empty set also. But what is S union T? Also a very good thing to use with these are called Venn diagrams. And what that helps us do is give us a pictorial representation of union and intersection. So for S union T, this is going to be equal to, this is the new set we're creating. So I'll just use a basket again. And it's going to be things that are in S or in T. What I'm going to do with that is I look and everything in S, I can just write out 1, 2, 3, 4, 5, 6, 7. And then I look at T, 2 is already in there, 4 is already in there, and 6 is already in there, so I don't have to put anything in there. And as I do that, I notice that what has happened there. What is this? So this is their union. What is that though? S. Oh, what's happened there? Well, it turns out T is already a subset of S. So this is useful to know, and a clever way of doing this is an immediate consequence of this is if T is a subset of S, their union is always the bigger one. What that says is, with the Venn diagram of what we're doing is, here's our universe of discourse, all the positive integers say. And then what we're going to have is S. Let's make S the blue one, and then T the orange one. Well, we had 2, 4, 6 inside T. And then S was 1, 2, 3, 4, 5, 6, 7. And that's S. So T is inside S. So in the Venn diagram, you get the egg with the yolk, essentially. What that tells us is these elements are already in there. And when you take as T being a subset of S and I take their union, it's always going to be the bigger set if I do this. So S union T will be S because I know T is a subset. If we do the reverse, before I do that, for number 2, what is S cap T going to be? I can use the same picture. Well, now starting from the picture, you can see the usefulness of Venn diagrams. Now I have to take anything that's only in S and in T. So is this in S and T? No, it's in S, but it's not in T. And neither is this, and neither is this, and neither is this. But 2 is in S and it's in T. 4 is in S and in T, and so is 6. So this is going to be 2, 4, 6, which happens to be what? The smaller guy, T. So if they're related as being subsets already, the union is always the larger one. Everything in OR, but these guys are already in S, and the intersection will be the smaller one. Let's do another one. Now we're going to do union of S and R and intersection of S and R. All right, for S and R, what we're going to do is the same thing. I'm going to draw S first, and then we're going to draw R. And the clever way to do this is, hopefully they're not, yeah, there we go. And then we're going to have something like this. And we'll call this one R and this one S. What I have to do is cleverly put all the values in there so you can see what this is trying to get at. But I have 9 is in R. I'll use orange for all of them. And then we have 3 and 5 and 7. And then we have 1, 2, 3, 4, 5, 6, 7. So those are all the values in S, and those are all the values in R. And now you can see where we're going to get at. Where do these intersect each other? Or where's the overlap? This thing is going to be the overlap. And so that's going to be our intersection guy. And then the union is always the dividing cell or the blastocyst at the end of cytokinesis when it's trying to divide. That will be the union of the two. So what am I going to get? The union of these things, again, is everything in S or in R. So first I write down all the things in S, 1, 2, 3, 4, 5, 6, 7. And then I ask myself, did I miss anything in R that's in there? Yes, 9, so I can add the 9. That's their union. Now their intersection has to be in both of them. And from the picture it becomes immediate, and that's why we call it intersection. This is the intersection of S and R. It's going to be the values that are in both of them, and that will be 3, 5, 7, the first 3 odd prime numbers. What happens here now is, in general, union creates a bigger set, and intersection is restricting, so it's going to create a smaller set from the 2 given sets in general. Now let's look at R and T. For the next 2, comparing R and T, their union is going to be anything in R or in T. So the easiest way to do this is things in R were 3, 5, 7, 9. And then things in T are 2, 4, and 6. Also notice that it's just a basket of objects, which are the avatars, one of the avatars of these positive integers, but it doesn't have to be in lexicographical ordering or in increasing or decreasing order. I don't really care. That's the basket, created a bigger set. So it was everything in here or in here. Now I look at the Venn diagram and you can see what's going to happen, and this is why we wanted the empty set. What's in both R and in T? Well, they have no overlap in the picture in the Venn diagram, and therefore this has to be nothing, but it had to create a set, so we've created the empty set in this intersection. Rational numbers have an infinite repeating decimal expansion. Irrational numbers have an infinite non-repeating decimal expansion. You can't both have a repeating expansion and a non-repeating expansion, so the intersection of those 2 sets are empty. That's where I'm going with the empty set. Now for the last one, let's consider what happens when you screw with the empty set. As a remark before I start, as a hint, you should be able to get both of these. The empty set is a subset of every set vacuously. If you're in the empty set, which is always false, then you're in that set. So this is vacuously true, the statement that the empty set is a subset of S for all sets S. And using 1 and 2, what is the intersection and union going to be? All right, for T union empty set, it's anything that's in T or in the empty set. There's nothing in the empty set, so it has to be, and we know it's a subset, it has to be the larger one. This is T, which will be specifically 2, 4, 6. What is in both the set that has nothing in it and in T? There is nothing in common, and we know that empty set is a subset of T, so it has to be the smaller one. This is the empty set. They have nothing in common. What does a set that has something in it and a set with nothing in it have in common? Nothing. Their intersection is the empty set. These are the operations we're going to use: union, intersection, subset, complement, and the empty set. Complement, you'll see, they didn't even give the irrational numbers a new symbol. They just called it the complement. Numbers that are real that are not rational. So we're going to get the notation right away. Let's do that. All right. The kinds of numbers and their set notation, essentially, and then I'll give you a little historical description of how we came to this conclusion. And then we'll show you the Matryoshka doll and the Venn diagram of all of these guys. this is a subset of this, this is a subset of this, this is a subset of this, this is a subset of this guy is the one they were like, well, these guys are so misbehaving, they're going to be just called irrationals, and they didn't even give it a new symbol. I would want it to be capital I, but they're like, no, just the complement of the rationals inside the real numbers, the bad guys. Who are they? Positive integers. Z, we'll get to that in a second. In German, it's Zahlen. So we use script Z for the symbol. I'm going to add the plus for the positive integers. So Z plus is just 1, 2, 3. And then in some books they will call the natural numbers this guy. And then this would be the whole numbers. So you might have also seen this as W, which is the whole numbers. Hashtag positive integers. What we're going to do next is Brahmagupta comes around in about 600 AD and he invents zero. Well, discovers zero. Invents it, discovers it. We'll see, discovered it. Everything's a discovery. The universe already put them in there. This is Kronecker. Die ganze Zahlen, liebe Gott gemacht, alles andere ist Menschenwerk. God created the integers. The rest is the work of man. So these guys are just there. Then what do? We invent zero or discover zero and start manipulating there. So we add zero. The natural numbers, we just added zero. And notice I can put that into our union notation. Every natural number is either zero or a positive integer. So it's the union of zero and the positive integers. Then what we do is we consider negatives. We start having commerce and these types of things. And not only did you want 6 apples, but you only had enough for 5. So you got all 6 apples, but now you owe negative amounts of apples or dollars. And so we get the notion of negatives. So the integers are the collection of 0 positive integers and the negative of positive integers. And this is their set. The ellipsis is going to be ... It continues indefinitely in both directions. Now squeezing in set builder notation. What set builder notation does is use the curly brackets, but when we have more complicated things, you say quantity x or elements x, or in this case elements r, such that is the vertical line is read as, and then the properties that r has. So in this case, what were the rational numbers, or why did they use q? Quotients of integers is essentially what they're doing, and you can't divide by 0. Brahmagupta found out when he created this. So what we have is rational numbers are ratios of m over n, where m can be any integer, but n has to be a positive integer, and I've cleverly done that where it can't be 0 now, so I've eliminated the case of dividing by 0. Irrational numbers are going to be the parasitic definition of this, numbers that are not rational, which is not very helpful, but we will see that this is uncountably larger than the rational numbers, and this is where everyone lives in the whole world. Name for me 5 irrational numbers. Exactly. You've only ever used rational numbers, but this one's much larger. And what are they? Numbers that can't ever be written as the ratio of 2 integers. The square root of 2, e, pi, the square root of 5, the golden ratio. And there's 5, I guess. But what are the real numbers? And we'll get to why this is true in a second using decimal expansion. And then we'll remind you what decimal expansion actually means. 123 means 1 group of 100, 2 groups of 10s, and 3 ones. But where do I get this conclusion? Now, the real numbers is the disjoint union of the rationals and irrationals. What that means is R is either every real number is either a rational number or an irrational number, and no number can be both rational and irrational, so the intersection of Q and Q complement is the empty set. So all real numbers are the disjoint union of rationals and irrationals. What that means is every real number, and how I'm going to get this intuitively for you is every number either has a repeating decimal expansion, and therefore if and only if you're rational, or it has an infinite non-repeating decimal expansion, which means by default you are irrational. And no number can both have a repeating expansion and a non-repeating expansion, so nobody's in this guy, this intersection. Let's do that specifically. All right, to give motivation as to why every real number is either rational or irrational, we need the notion of decimal expansion. And then let's start from what the definition is for a positive integer. If I have a whole number, what Brahmagupta and Aryabhata also discover right then is, and this is why we get this, every country in the world has 1 or more languages, but then you look at when we start doing mathematics, everyone is using all of the same notation. You're using decimal notation, probably because we have 10 digits, but also how did this become that all of mathematics and every number avatar that we use, we can use decimal notation and everybody chooses to? Well, what they realize is This is called a positional number system, and what that cleverly does is I don't need to create new symbols every time I want to get larger and larger magnitudes of numbers. And so what cleverly this is, and we'll remind you for positive integers, is the notation for a positive integer is going to be n is equal to, I know and we have to index, but it's dk minus 1 all the way to d0 base 10. Usually when we're doing different bases, you have to write the base, because in binary it would be base 2, and in hexadecimal it would be base 16 when we're using computers and those types of things. But classically we use base 10, and if we're not using any other bases or transforming between them, we're just going to get rid of that and just write it like this. What does that really mean? All we have to do is pick each of the di's to be an element of some set. And what are the set? 0, which he discovers, the placeholder, and then 1, 2, 3, 4, 5, 6, 7, 8, 10 minus 1, 9. Now all I have to do is create, and we use the Hindu Arabic symbols for all of these. I needed a symbol for 1 and 2 and 3 up to 9, and the symbol for 0, which they get. And now the clever idea is each of these comes from here, and then their position actually tells us which power of 10 they're multiplied by, and then we add that thing up, and that gives us the number of apples in the basket. So this symbol actually means this number times 10 to the k, and then this one is going to be times 10 to the 1, all the way down to this one is multiplied by 10 to the 0, which is a 1, and then we add these numbers up. I know this is a horrible notation, so right below here's an example. 1, 2, 3 is the words in our language are still this. 1,000 means 10 cubed, 100 means 10 squared, tens means 10 to the 1, and the 1 spot is 10 to the 0 actually. So what is 123? That's one group of hundreds, 10 squared, plus two groups of tens, 1 to 10 to the 1, and 3 ones, 3 times 10 to the 0. This is what 123 in our notation represents. This positional system tells us that I can create any arbitrarily large number. Now the question that we want to ask ourselves is, which you don't, once I start inventing new types of numbers, can and how do I represent them in decimal notation? Does every real number have a decimal notation? Well, if we think that, and we'll get to a couple of theorems, every number is rational or irrational, how do I find the decimal expansion of rational numbers, fractions of integers, and how do I find the decimal expansion of irrational numbers? We're going to use successive approximation of the rational ones to get at the irrational ones. So, yes, it turns out every number can be written in a decimal avatar, and this is a non-trivial game for the irrational ones, but this one will give you some kind of Pavlovian nerve in your brain from grade school. We're going to use long division, and then I'll show you the other way that they usually don't show you. If I give you 0.6 repeating, how do you know that's 2/3? How do I get the fractional avatar from the repeating avatar? If you give me the fractional avatar, I'll use long division to get the repeating avatar. But how do we go back and forth? Let's get at that. All right, we're going to use some heavy machinery. You can look them up, or I'll tag or I'll pin the PDF of the proof of these two statements if you really want. But the intellectual idea and the peace of mind that it's going to give us is what I want from these two statements. Theorem 1 tells me that every real number, whatever those are still, can actually be written uniquely as a decimal expansion form. So that's existence and uniqueness. Every number can have a decimal expansion, and there's not more than one way to do it. This will be our horrible notation. In particular, if we have a whole number, it's just that first part, but then we have all of a sudden the decimal point, and then these other guys. What does the decimal point mean? Actually, what the decimal point is indicating is the powers of 10 become negative. So if r is this notation, what that means is it's the same notation if it was a positive integer, and then here's where the decimal point comes in right here, is c1 times 10 to the minus 1. And remember, 10 to the minus 1 is 1 over 10. It's the reciprocal. So this is c1 over 10 plus c2 over 10 squared plus c3 over 10 cubed. But the exponent is negative, and so that's what the decimal point is giving us. It tells us when the powers of 10 become negative. And what this theorem says is every number can be written as a unique decimal expansion. And in particular, how do we get that there are two types of real numbers? Well, because I now know every real number can be written in a decimal expansion, I use this theorem 2 to say that if you're rational, then you have an infinite repeating decimal expansion, and if you have an infinite repeating decimal expansion, you have to be a rational number, or the ratio of two integers. And these are the two forms, the fractional avatar and the decimal avatar of a number which is rational. So what does the theorem say? A number r is rational if and only if it has an infinite repeating decimal expansion. And what will that look like? There will be some L where in the long division where we truncate this, you get the same remainder. I'll show you in a second. But then I get a pattern, and classically we put the bar over that. That actually means that this is going to give us C2 dot 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 CL, and then it's going to repeat in blocks C1, C2 dot 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 CL, and then it's just going to keep repeating over and over and over again. And so we write bar to mean that that pattern of L coefficients are just going to repeat over and over and over again ad infinitum. Let's do an example. All right, example 2 is going to go back and forth between rational numbers and their two types of avatars. Basically, we're proving theorem 2 without doing the rigorous indices horrible nightmare. Basically, what I'm going to do is, if I have rational numbers, which means rational numbers are the ratio of two integers, so I have 2/3 and 2/7, why is it that there must be a repeating decimal expansion for those guys? And conversely, if I take two numbers which have a repeating decimal expansion, why can't I always write them as the ratio of two integers and therefore they're rational? So you're rational if and only if you have a repeating expansion. In particular, these are the two different avatars of the same number, 0.6 repeating indefinitely, which happens to be 2/3. Let's get to it. 1. This one you've seen from grade school, so I'll just remind you. I'm dividing 3 into 2. What that does for me is, what you have to do to get this one, the application is, I don't know how many I need, I don't know what the repeating pattern is, I do, it's only one long. But if I don't know, and then I just start playing this game, also what's useful is to list the multiples of 3 first, 3, 6, 9, 12, 15, dot, 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 up to times 9. But I know I won't need most of these. What are we going to do? And this would be times 1, times 2, times 3, times 4, times 5. Actually, I'll probably need the next one. Why did I do that? Because this is the first tip too, and you'll see when we get much larger numbers of the base and you don't know the multiples. If I'm going to do this one, 17/2, what's the first multiple of 17 that goes into 200 without going over? You're like, I don't know. And that's the game of why you didn't like long division. If you list them first, then you don't have this problem. So what I'm asking myself is, and this one's fairly trivial, how many times does 3 go into 2 without going over? 0 times. Usually they don't write that one in there, but technically what I've done is, and then 3 times 0 is 0, and then I subtract, and I get 2, and then I bring the next 0 down. And I put the decimal point right above where it was always. Now you can see all the pattern. I got 20 again. Now I ask myself, how many times does 3 go into 20 without going over? Well, right here, 6 is good, but 7 is too much. 3 times 7 spilled over, and this is the game. If you list them, and especially when you have larger numbers, then that game becomes extremely quick. So it's a 6 that goes here, and then the outcome I already have, 18. Then I subtract, and oh look, and I bring another 0 down. As soon as that happens, we know that we have the repeating pattern. Just in case, if you don't, I'll do it a couple more times just so I can get 666 basically. But how many times does 3 go into 20 if you didn't notice it? 6 again, and then I'm going to get 18. I subtract, I get a 2, I bring another 0 down, oh, and it's 6, and it just seems like it's going to just keep repeating over and over again. How do we write that? This tells me that 2/3 is equal to 0.666 repeating indefinitely, or the way we write this in the notation is 2/3 happens to be 0.6 repeating indefinitely. If you are a fraction of two integers, then you have an infinite repeating decimal expansion. That's half of the theorem with an example. Let's do it for a slightly larger number. When you divide by 7, it never has 3s or 6s or 9s in the expansion. It'll have all the other numbers, so I need 6 long, and it'll have a 1 and a 2 and a 4 and a 5 and a 7 and an 8 involved in there. You'll see. So what am I doing now? I'm dividing 7 into 2. This time 1, 2, 3, 4, 5, 6, or I need a bunch of zeros, I don't know how many. I write out the multiples of 7 again. I get 7, 14, 21, 28, 35, 42. Do I need any more of them? Probably 49, 56, 63. Then we have times 1, times 2, times 3, times 4, times 5, times 6, times 7, times 8, times 9. Everyone always says, you're just wasting so much time, and why do you do that every time? because it makes it the next part of the game a whole lot easier. Same thing now. What am I going to get? Again, the same thing. 0, subtract, I get 2, I get 20. Now I ask myself, what's the nearest multiple of 7 that doesn't go over 20? Right here, 2. And I already have the outcome, 14. I subtract, 20 minus 14 is 6, bring a 0 down, I get 60. How many times does 7 multiples of 7 go into 60 without going over? I don't like this game, but it's going to be 8. I already know what the outcome is, 8, and I have the outcome as 56. Minus 60 minus this is 4, bring a 0 down, I have 40. How many times I look? 5. 35. I subtract, I get 50. How many times does it go into the 7? And I'm going to get 49. Subtract, I get 10. It goes into there once, and I get 7, and I get 30. And then I'm going to get, how many times does it go into 30? Oh, a 4, and I'm going to get 28. And then I'm going to get a 2. And look, I got the 20 again, so I can stop. And this will be the repeating pattern. Notice that it has all the numbers except for 3 and 6 and 9 in there. It's always going to do that. That's for a different lecture. But what does that tell us? 2 over 7 now is 0.285714, repeating indefinitely. If you are the ratio of two integers, I can use long division to always create an infinite repeating expansion. So you have two different avatars, the fractional avatar and the decimal repeating avatar. Now let's do the reverse. How do you go from this and know that it's 2/3? I turn 2/3 into the 0.6 repeating. How do I start with 0.6 repeating and turn it back into the fraction? The key to ingenuity is hiding your sources. Steal it from me. So I have the decimal repeating avatar of this number, which happens to be 2/3. How do I get this? The clever idea is using algebra. I'm going to call it something, x. And then we're going to use a few properties. Now what I'm cleverly going to do is technically multiply by 10 over 10, or multiply both sides by 10. What does 10x equal? My base is 10, that's how I know to multiply by 10. So the step 1 is write it as x. And then multiply by appropriate powers of 10 to get the same repeating pattern. I want two numbers that have the infinite 6's, and then I can subtract them and get rid of all the infinite 6's. So if I multiply by 10, I'm going to get, what if I multiply both sides of this by 10? Multiplying this by 10 shifts this to the right one, and so I'm going to get 6.6 repeating. Aha! And so what does that tell us? I write these cleverly. I write this as 10x equals 6.6 repeating. That's one number that has the repeating part 6. And then I have just x, which is 0.6 repeating. I have two numbers that have the same repeating part. Now I subtract them. And I get 10x's minus 1x is 9x's. These are going to cancel. And then we're going to equal 6 minus 0 is 6. Oh, and what does that say? Solve for x. This is one equation and one unknown. Then a is non-zero, which is a 9. I can invert, and this tells me that x is 6 over 9. And this is actually the cancellation. This is 3 times 2, 3 times 3, so I can cancel. And in lowest terms, this is the fraction 2/3. So I can go from the repeating part to get the fractional avatar every time. Let's do another one where the repeating part is only on the 2, so I won't be able to use x itself. I'm going to have to use a much more difficult scenario where I have to, from x, which I can't use in this one, I have to create two numbers by multiplying by different powers of 10 to get the same repeating part. Let's do that. All right, x now is 0.12 repeating, and remember, careful, I always have to write in brackets on the exams. The bar is only on the 2, not on the 1. So what is this? Write it out for yourself. This is 1, 2, 2, 2, 2, 2. It's not 0.121212. That's an entirely different number. So that's not what it is. The bar is only on the 2. It's a 1 and then a bunch of 2's for infinity. That's a lot of 2's. Countably many 2's though. Now what do I do with that? Because in the first one, the repeating part was right next to the decimal point, I can actually use x. But now the repeating part is 1 away. So I'm going to have to move the decimal 1 to get a number 1.2 repeating. And then I'm going to have to move it 2 spots to get 12.2 repeating. So I want two numbers from this number which have the same repeating part. What do I get? Let's do 100x. First, so it's on the top. I already know where I'm going with this. So if I multiply both sides by 100, I'll get 100x, and then this is going to move it 2 spots, and I'm going to get 12.2 repeating. If I multiply by 10, it'll move it 1, but I have the repeating part. So then I want to multiply by 10x, and that's going to give me 1.2 repeating. Either way, I created from my x, I created two numbers that have the same repeating part. Now I can subtract, and those will go away. What does that give me? 90x equals 11. I solve, and this says x equals 90 or 11 over 90. You don't have to, but this is in lowest terms. 90 is 2s and 3s and 5s, and this guy is an 11, so it's in lowest terms. You don't have to do that at first. But the moral of the story is, if you have a fractional avatar, you can always write it as a repeating decimal avatar, and if you have a repeating decimal avatar, you can always write it as a fractional avatar. Numbers are rational if and only have to have an infinite repeating decimal expansion. Now to finish off this first video, finally, you're like, that was a whole lot about numbers. Yeah, do you know what a real number is in your own words? And then the numbers don't stop. Complex numbers, Hamiltonian numbers, octonian numbers, Betty numbers, what are all those guys? Different videos, you'll see one day. How do I get the infinite non-repeating decimal expansion of irrational numbers? Or can I, and the theorem already told me I can, so I know I can take pi, and I know you've seen it. His approximate decimal avatar is 3.14. 1592, 65358. But how are they getting these? Remember, that says 3 times 10 to the 1 plus 1 times 10 to the minus 1 plus 4 times 10 to the minus 2. How are they getting these coefficients, and how are they getting the decimal expansion? You won't be able to see this as engineers until we do Math 101 or Engineering 101, where we do Engineering Calculus 2, and I get the power series representation, and then I will get at these fancy guys. The moral of the story is, this is extremely hard and a non-trivial game, but the goal is the name of what we call them. We approximate or find the decimal expansion of irrational ones, the ones that could never have a nice closed form, and they just have an infinite non-repeating pattern. Those irrational numbers can be successively approximated with the rational numbers. Let's play that game once for the square root of numbers. All right, example 3 to finish off. The moral of the story is to find the infinite non-repeating decimal expansion of irrational numbers is a non-trivial thing. First of all, are there irrational numbers? So it's an exercise for you to prove that classically the square root of 2 is an irrational number, or the square root of 5 is an irrational number, or the square root of any prime is irrational, or in fact the square root of any non-perfect square, the square root of 10 is approximately pi, coincidentally, 3.15, I believe, or 16. But how do I get these we now know are irrational numbers? I'm going to start out by assuming this guy is an irrational number. You prove it for me. But once I know that, how do I find the decimal expansion of the square root of 5? How do I know it's 2.236? Because I've done this before. But how does your calculator know this, or where are they getting this from? The Babylonians is the first appearance of this, and this is circa 3,500 years ago. They already have a derivation for this. Often this is called Newton's method or something else, but I think the Babylonians had it first. What are they doing? And I'll give you clever tricks along the way. First of all, they have to make an initial guess, and what they're doing is they're pretending they have a box of two numbers. This is an irrational number. I can never write it down exactly, but what they're guessing is that we're going to get an underestimate and an overestimate in each step, and we're pretending that the multiplication of those two numbers, we're assuming that x0 is approximately the square root of n, and y0 is approximately the square root of n. So then when I multiply those two things together, I get exactly root n times root n, which is n. They're both the square root of n. But in that clever scenario now, what am I doing? In each step, what I first have to do is get an initial guess. And how do I do that? I'll show you in a second. Once we have the first guess, what the Babylonians noticed is, if these are my first two guesses and I have an interval on the real number line, how do I get a better, and those are going to start off with really bad approximations to their square root of 5, how do I get a better approximation and an iterative method to get closer and closer to it and get arbitrarily close to the decimal expansion of this number? It turns out that the midpoint of an interval is the average of the two endpoints. So the midpoint of this interval is going to be x0 plus y0 over 2. And that's the guess that he makes. For the next guess as the better approximation of these two guesses, I can get closer to that by knowing that this value is always in the interior and it's going to be much closer to the square root of 5. So my next guess is x1 will be the average of the previous guesses, and then we're always assuming that x1 times y1 is n. So y1 will be n over x1. And then in the kth step, we're doing this iteratively. In the kth step, xk is the average of the previous two guesses. That'll get me closer. And then yk will just be n over xk. And then I get an under and over estimate every time. I can get closer and closer and squeeze into the approximation. Once I think I'm sufficiently close, I'm going to have two fractional avatars of an overestimate and an underestimate. I look at using long division of their decimal expansion of those two numbers, and then I subtract wherever I get zeros means that they were correct to those decimal points, and we get an approximation of irrational numbers. What? Approximating irrationals with rationals is a non-trivial game. Let's try it once for these. How do I get an initial approximate guess for the square root of 5? What I ask myself is, I have the number n is 5. Start with this number. I want to know a number larger than 5 and less than 5 that are perfect squares. So it turns out that 4 is 2 squared. And 9 is 3 squared. Now if I square root this whole thing, it preserves the order, and that will say that 2 is less than the square root of 5 is less than 3. And this is already given, though bad, because I don't have any of the decimal points yet, but this has already given us an approximation to what root 5 is. I know it has to be approximately equal to 2.C1, C2, C3. I know the one spot is a 2 because it's strictly larger than 2 and it's strictly less than 3, so it has to be between 2 and 3 strictly. That means I've already found the one spot of this decimal expansion. 2.236 is what it's going to be. How do I find these guys? Well, what I'm going to do is, this was my first guess, this is my outer guess. What we're now going to do is to do step 1, I'm going to look at the average of those two guys and get closer to that value. And so what's the middle of those two guys? 5 over 2. Let's check that out. So what do I do with that? Once I have my first initial guess, that now we know that 2 is less than root 5 is less than 3. This was my x0 and this is my y0. So step 1. Once I have my initial guess, I just iterate this over and over and over again. Ad infinitum or ad nauseum, whichever one comes first. Nauseum always comes first. So I'm going to get x1 is x0 plus y0 over 2, which is going to be what? This will be 2 plus 3 over 2, which is 5 over 2. The average, the midpoint of that, 2.5. Then what is y1? It is always n over x1, which in our case will be 5 over 5 over 2, which is 2. So it flipped us and it gave us that guy, which is also in this one weird one, x1, but this is now, or y1, and this is x1. What we've now done is, we now, at first, in the first guess, we knew that root 5 was somewhere between 2 and 3. Now what we've done with that second guess, we now know it's somewhere between 2 and 2.5. It's 2.236, so we're getting closer and closer. And this is my y1. This is my x1. So I keep going, and I know that the decimal expansion of this is 2.0 and this is 2.5, long division. Step 2. x2 is going to be x1 plus y1 over 2, the average of the previous, which is always going to be 1/2. Now we have to do fractional computations. This is 1/2 times, what do we have? 5 over 2 plus 2 over 1. I need a common denominator, so I multiply by 2. This is going to give me 1/2 times 4 plus 5 is 9 over 2, which is going to give me 9 over 4, which is 8 over 4 plus 1/4, which is 2.25 in its decimal avatar. 2 1/4. Then y2 is going to always be n over x2, which is going to be 5 over 9 over 4, which is 5 over 1 times 4 over 9, which is 20 over 9, which I can also use decimal expansion or long division to find the decimal expansion of this guy. It's not too close yet, so I'm going to do at least one more step. Let's move that up. All right, one more step, and then we can give you an approximation to 3 places anyways of this guy. The work's not done yet. This is the clever idea of iterating this. Put it in a computer, make it do it 100 times, and you can get a really good approximation. For here, what do I have? This will be 1/2 x2 was 9 over 4 plus y2, which is 20 over 9, which is 1/2. I need a common denominator, so I have to multiply it. It'll always be 9 squared, so 9 over 9 times 9 over 4 plus 20 over 9 times 4 over 4. I get a common denominator. This is going to be 1/2 81 plus 80 over 36, which is 161 over 72, 2 times 36. I know the numbers get really big really fast. Try to do this with the square root of 15. The numbers get big fast. So y3 is always going to be n over x3, which n was 5 over 161 over 72, which is going to be 5 over 1 multiplied by 72 over 161. Oh, the Mayans like that. That was one of their short calendars. So 360 plus 5 unnamed days. So we get these two approximations. This is y3 and this is x3. I assume that these are a fairly good approximation. Now what do I do those? What that tells me is this. All right, now that we've done approximations to where we think we've got we've done enough steps to where we think we've got a reasonable approximation to this. I've done this before, so I know that when we do it at step 3, it actually gives us, it doesn't match in step 3, it'll give you 3 decimal places. This converges fairly slowly, actually, this algorithm to the right value. But if you do this for 1,000 times, it will eventually get and converge closer and closer to the square root of 5. If we do step 3, it gave us an approximation to 3 places. How do I know this? Well, it gave me, this was x3 and this was y3. They flip their roles, but you always get an underestimate of root 5 and an overestimate, and they're getting closer and closer. So what I now do is I have to turn those 2 fractions that I have into their decimal avatars, and I do that using long division. Here again is when the numbers get big and I have to divide. What's the closest multiple of 161 that goes into 360 without going over? It's like, I don't know, but then I look and I'm like, oh, it's a 2. So then I start doing that and then I can get in there. What's the nearest multiple of 161 that goes into 970 without going over? It's like, I have no idea. Yeah, there it is, 6, 966, and I already have the outcome. So by listing these first makes long division a whole lot, for lack of a better word, fun. It is fun if you know how to do it correctly. Therefore, I use the long division on those 2 approximations, and I notice that I go to 4 spots and then they start differing in the 4th decimal spot. That means that they match in the first 3 decimal spots, so correct to 3 decimal places, the square root of 5 is approximately 2.236. Why would I want to know this? Well, I actually want to know what the approximation to the golden ratio is. What's the golden ratio? It is 1 plus root 5 over 2 is the algebraic formula for that. So now I can, if I have the decimal expansion of root 5, I can get at the approximate value of the golden ratio. Let's see how to do that. All right, so for the golden ratio, I have a video on the golden ratio if you want to see what that is or where they get it from. It's a geometric construction. You have a single line segment, and what we want to do is cut that segment in one cut, so unequal cuts, so that we call this 1, and so that the ratio of the whole segment to the larger segment is equal to the ratio of the larger segment to the shorter segment. When we do that, we get x plus 1, the whole length, over x should equal x over 1. This gives us the quadratic x squared minus x minus 1 equals 0. When we solve that, the positive root of that is 1 plus root 5 over 2, so I get an algebraic expression for the golden ratio, but it involves this irrational number, root 5, which if I want to know what the decimal expansion of the golden ratio is, I need to know what the decimal expansion of root 5 is. Once I've approximated the decimal expansion of root 5, I know that it's approximately 161 over 72. That means that the golden ratio is 1/2 1 plus this guy. Simplifying that fraction, I get the golden ratio is approximately equal to 233 over 144. What that tells me is, again, I use long division. I have to divide 144 into 233. I list the multiples of 144 first, and I start doing that. And when I do that, I get the fact that the 233 divided by 144 is, in fact, 1.618, 3 spots. Therefore, the golden ratio corrected 3 decimal places is equal to 1.618. Please subscribe right here. Hit the notification bell. I'll see you next time.